Good afternoon, boys and girls, ladies and gents. Welcome to Algebra 2. The number e in the natural log today. Yes, the number e. That is not a mistake. There are many numbers in mathematics that are more important than others because they find so many uses in either math or science. Good examples of important numbers are 0, 1, I, and pi, which we've already learned about. But in this lesson, you'll be introduced to an important new number given the letter E for its, some say inventor, I would say discoverer. Leonard Euler is an age-old debate. Is math invented or discovered? I would say it's discovered because we're finding ways to model our universe with symbols and representations. Uh, but that's neither here nor there. This number plays a crucial role in calculus and more generally in just modeling exponential phenomena and things that grow exponentially. So, three facts to know about E. One, it's irrational, just like pi, meaning its decimal goes on forever without repeating any set pattern. It's unpredictable in that sense. It's approximately 2.72, and you can evaluate it on any modern scientific calculator to see many more digits of it. And it's used in exponential modeling. So the question here, 63, when you consider the fact that E is about 2.72, then E to the x would be 2.72-ish to the x, which has got to be pretty similar to 2 to the x or 3 to the x, which we've already seen. Exponential growth looks like that. So this is our guy. Okay, now what about inverses? So because it's so important, its inverse is also important. We call this the natural log because this occurs naturally, exponential growth. So all you got to do is remember to calculate an inverse. You switch x and y. So I'm going to take y equals e to the x, switch the x and y. And again, I liked the expression with the base on the left. So I'm going to move the y to the other side, then switch them. And then I can just drop my base to put it in log form. And then remember the old switcheroo. And I got y equals log base e of x. Now, this is so important that we've come up with a new symbol for it. But it's important to know that this log base e of x means this ln of x. Ln is just short for natural logarithm. I believe it starts with L just to not confuse it or to link it with other logs because natural logarithm, maybe it's logarithm naturel in some other language. That is something I don't know. Moving on, the natural log, like all other logs, gives an exponent as its output. This is very important for this next part. In fact, it gives the power that we must raise e to in order to get the input. All right, so in this case, what is our input? It's e. So the question just becomes, what power do I have to raise e to get e? So we can rewrite this very simply, kind of like this. What power do I have to raise e to get e? Well, anything to the first power is 1. Is itself, excuse me, not 1, itself. So the natural log of e is just 1. What about here? What power do I need to raise e to get 1? Well, this is that old property that anything to the 0 power is 1. So if I were to put a 0 here and raise e to the 0 power, even though e is irrational, I'm still going to get 1. So the natural log of 1 is 0. What about here? E to the blank power, and you can start to think of this as a fill in the blank question or a variable question. Just put a variable there as well. But this one should be crazy obvious. What power do I need to raise e to get e to the 5th power? Well, 5. And then lastly, don't forget here that radical e equals e to the 1/2. So this question becomes, hey, what power do I need to raise e to get e to the 1/2? Well, that would be 1/2, 0.5. You can check these. Go to Desmos and check them in that miscellaneous button in the functions menu over there. You'll see the LN natural log button. All right, let's see here, moving on. Okay, these are properties that we've already seen. I believe, yep, it's on page 28. These are the same three properties from page 28 that govern all logs because natural log is a log, it's just a special log. All right. Natural log equals log base E. I don't know, because I don't need the of x for this, right? But that's the idea there. So all these could be rewritten as the natural or the log base E of x times y equals log base E of x plus log base E of y and so on. But I'm just going to continue. That means we can use these properties. Remember, when we see a minus sign, that's related to, I'm sorry, division is related to a minus. So I have natural log of x to the third power minus a separate natural log of e to the second. We also learned a property that, hey, I can bring these powers out front. That's this third property here. So I have 3 times the natural log of x minus, hey, we just did this one, or at least we did e to the 5th power in the previous page, but that's just 2. Now, another way to look at it would be, and this is off to the side, you could just go, okay, I could bring that 2 out front just like I did with the 3 and say, okay, I also learned that the natural log of e is 1, so it's 2 times 1. Either way, it's 2. Which brings us to choice 2. Lastly, very often E is involved in exponential modeling of both increasing and decreasing quantities. So here we have a hot liquid. Hopefully it's a delicious coffee in a room whose temperature is constant. Its temperature can be modeled using an exponential function. T of M equals 101 E to the negative 0.03 M plus 67. The temperature T is in degrees Fahrenheit as a function of the number of minutes M it has been cooling. What is the temperature, the initial temperature of the water? Initial temperature, when did it begin? All right, at time equals 0. This is simple, just plug in 0. Now, if I want to be safe, I'm just going to go right to a calculator from there. But we could use a little bit of our brain power here and say, hey, that would just be 0. Then that would mean we have e to the 0 power. Anything to the 0 power is 1. So we have 101 times 1 plus 67, which is going to be 101 plus 67, which is going to be 168 degrees Fahrenheit. How do you interpret the statement that T of 60 equals 83.7? This, whenever you see interpret, they mean they want you to put it in words in the context of the story. So in the context of the story, we have to talk about temperature, we have to talk about time. So I would say at the 60th minute mark, the temperature was 83.7 degrees Fahrenheit. All right, part C. Let's get into some algebra. Let's see. Determine algebraically when the temperature of the liquid will reach 100 degrees. So we essentially want the output. We want T to equal 100. So we have 101 E to the negative 0.03 M plus 67 equals 100. Okay, inverse operation time. Remember, to solve any exponential, we're going to isolate the exponential part, then we're going to use logarithms to eliminate that exponential aspect to invert it. So we got 101 e to the negative 0.03 m so far equals 33. We're going to then divide by 101 to cancel this out. And we'll have e to the negative 0.03 m equals, and I just leave these in fraction form. It's just easier to work with and get a more precise value. Next, we're just going to bring down that e as the base. Remember, it's the base of this exponential expression. So it's going to become the base of the log. Hey, that's the natural log. Then we perform the old exponential to log switcheroo. Okay, now some people go to a calculator right away, or they convert this to the natural log because that's just the symbol for what we see above, and get a decimal value. I don't. I'd much rather continue one more step of inverse operations and say, okay, whatever I get is going to equal negative 0.03 times m. I'm interested in m, so I kind of want to just create a formula for m. And so all that would be is dividing, all right? So essentially what I'm just going to say is, and I'm running out of room here, so let me eliminate that and say, okay, so what that means is that m equals whatever I get when I take the natural log of 33/100 and divide it by negative 0.03. And so I went ahead and calculated this on Desmos, and I've got approximately 37.3 minutes. Let's see if I can pull that up for you. That's there, this first calculation. Cool. Let me copy that and embed it. And we're back. How much time we got left? 12 minutes. Okay, we're doing good, except that OneNote is freezing. Okay, take a sec, OneNote. I believe in you. And we're back. All right. Okay, lastly, on average, how many degrees are lost per minute over the interval from 10 to 30 minutes? For that, we're going to create a table of values. Essentially, I just need inputs and outputs. So I'm going to plug in 10, and I'm going to plug in 30. And the beauty, this is on average. This is a sneaky way of asking an average rate of change question without saying average rate of change. But that's what they're asking for. They're essentially asking for average rate of change. So we don't care about what's happening in the middle. We're just treating it as if it was a straight line connecting the points. 10 and its output, which also already calculated for you here. Lines 3 and 4, you'll see. If you define a function in Desmos, you can then just evaluate it. And then there's my final calculation there in the event that we run out of time, but I think we're doing okay. Yep. So when we plug in 10 to our equation, we get 141.8. When we plug in 30, we get 108.1. And then average rate of change, we're just gonna subtract those. So you can do it like this, or you can do it the way I did it on Desmos, which would just be more precise because it's gonna take the exact values for these. But either way, we're gonna get roughly negative 1.7 when rounding to the nearest tenth. So the question is how many degrees are lost. So I'm going to kind of drop that negative sign and just say approximately 1.7 degrees Fahrenheit are lost every minute, but not forever. This is not a linear thing. So I'm just going to say over the specific interval that they asked about from 10 to 30. And that'll do. All right, that's all the time we have.